All right. Hi, everyone. Welcome to the MTV Nuclear Engineering Summer School. I'm Sarah Pozzi. I'm a professor here at the University of Michigan in the United States, and it's my pleasure to welcome all of you to this program. The Consortium for Monitoring Technology and Verification is a group of 14 universities that work together with 13 national laboratories in the United States to work on nuclear security. So we work on new technologies that can help make the world safer through nuclear security. And as a part of this consortium, we're offering the Nuclear Engineering Summer School. The summer school consists of lectures held over Zoom webinar, which is how we are coming to you today. And it covers different course topics, general nuclear topics, detection of radiation, both gamma ray and neutron, topics in active interrogation, Monte Carlo modeling and simulation, radiation imaging, fission studies, and special applications of nuclear. You can find the full schedule online at the MTV website, mtv.engine.umich.edu. So we hope that you will join us. These lectures will happen Tuesday, Wednesday, and Thursday at 1 p.m. through 2 p.m. Eastern Time. So I'm really happy to announce that we have 667 attendees currently registered for our summer school. And you can see the breakdown of the registrants in the pie chart below. So we have postdocs, PhD students, master students, undergraduate, high school students, 7, so welcome all the high school students, and professionals. At the completion of our summer school, we will issue a certificate. In order to be awarded a certificate, you must attend 80% of the lectures over the summer. So for that reason, we need you to log on to the Zoom meeting using the same email every time and use the same name so that we can track you as we have many participants. So change your name to the same consistent name every time you log in. Also, Courtney will be helping with tracking. So if you have any questions, you can email her at the email address shown here. So with that, I'd like to thank the sponsors, and it's my pleasure to introduce the first speaker of our summer school. The first speaker will be Farah Rafi, and Farah is a PhD student here at the University of Michigan, and she will be talking to you about the fundamental nuclear forces, and her work and research concerns the electronics of readout systems for imaging systems using CZT semiconductor detectors. And she works on the ASICs for these detectors. She is advised by Professor Zhang He, who is my colleague here at the University of Michigan. So Farah, when you're ready, please go ahead. You can share your slides.
Okay, can everyone see the slides and hear me okay?
Yes.
Okay, perfect. Let me just hide this. Okay, hi everybody. Thank you, Professor Pozzi, for that introduction. My name is Farah, and today I'll be giving you a talk on nuclear structure and forces. So essentially, this will be an introductory overview of all of the nuclear physics behind the concepts that will be described throughout this entire lecture series. So hopefully by the end of my talk, you will have some sort of background and idea of what nuclear physics is, and you can hopefully have a good understanding of the rest of the lecture series. So with that, let's get started. First, I'll just give you a brief outline of my talk. So first, I'll talk about the foundations of nuclear and atomic structure. And then I'll go into elements and isotopes. And then I'll talk about 3 nuclear models. And finally, I'll go through some decay and scattering processes. So first, I'll start with the foundations of nuclear and atomic structure. First, I want to talk a bit about the nuclear scale of things. We're going to start at the very top of this hierarchy with matter. Matter is composed of a bunch of molecules bounded together. And a molecule is on the scale of about 10 to the minus 9 meters. While a molecule is composed of 2 or more atoms bonded together. And an atom is on the scale of about 10 to the minus 10 meters. Now, if we zoom into this center of the atom, we have the nucleus. A nucleus is a bunch of protons and neutrons that are being held together by the strong force, which I will talk about later on in these slides. And the nucleus is on the scale of about 10 to the minus 15 meters. Now, if we zoom into one of the components of this nucleus, we have a nucleon. A nucleon is either a proton or a neutron, and it's on the scale of also about 10 to the minus 15 meters, a bit smaller. And now, if we zoom into another component of this nucleon, we have a quark, which is on the scale of about 10 to the minus 18 meters. A quark is a fundamental particle that makes up protons and neutrons, so it is the smallest constituent of matter. And in my talk, I will basically start with the quark and then go through talking about the nucleon and the nucleus and the atom and sort of end at the atom. So we'll just talk about basically these 4 components here. And we'll try to build up a picture of the nucleus and the atom so that we can talk more about some complicated nuclear physics. So with that, let's start by looking at the standard model. So this table might seem a little bit daunting if you've never seen it before, but I'm going to simplify it for you as much as I can. So the standard model is a framework that describes the fundamental particles and all of their interactions. On the left side here, we have fermions. These are the building blocks of matter. And on the right side, we have bosons, and these are force carriers. And if you've never heard of this before, it's going to sound very strange to you, but I will describe this in detail in the next slide. Within these fermions, on the left side here, in the purple, we have quarks. These sort of build nuclear matter. And in the green, we have leptons, which build atomic matter. You'll also notice that within the fermions, there are 3 generations of matter. There's that first column is the first generation, and then we have the second generation and the third generation. And what we'll find is that higher generations tend to be much more massive and less stable, and they typically decay into particles of the first generation. They have a very short half-life of about 1 nanosecond or less. And so we'll find that all stable matter in the universe is made out of particles that belong to this first generation. And for this reason, in this talk and for this entire lecture series, I believe, we will basically just look at this first generation of matter. So no need to worry about generations 2 and 3. We're just going to look at the up quark, the down quark, the electron, and the neutrino. As for the force carriers, we're going to ignore the Higgs because it's sort of out of the energy scale that we're interested in. So we're just going to look at the gauge bosons. So hopefully I've kind of simplified this table for you. And now we'll go through each of these components in detail, starting with the bosons. There are 4 fundamental forces, and these forces are mediated by these bosons that we talked about earlier. There's the gluon, the photon, the Z boson, and the W boson. There's also this other potential particle called the graviton. It's hypothesized, but I'll talk a bit more about this later. First, we'll start with the strong force. This is the strongest of the forces, and I'll kind of go in order of strongest to weakest force. So the strong force is mediated by the gluon, and this force binds quarks together within the protons and the neutrons here. And I'll talk more in detail about this in a bit, if that's still confusing. Next, the electromagnetic force is mediated by the photon. And so I'm sure most of you are familiar with this force. Essentially, when charges are the same, they tend to repel one another. And when they are opposite, they tend to attract one another. And this force is responsible for light and electromagnetic interactions. The next force is the weak force. This is probably the least intuitive of all the forces. It's mediated by the W and the Z bosons. The Z boson is neutral, and the W boson can have a charge. And this force essentially is responsible for the radioactive decay of atoms and fission and fusion. And one example that I will talk about in more detail later on in these slides is the beta minus decay. So in this decay, the neutron turns into a proton, and in this process, a W minus boson is emitted. So it's able to make sure that this decay process is even possible. And finally, we have the gravitational force. This is probably the most intuitive of the forces. In this force, two bodies are attracted to one another because of their difference in mass. And it is extremely weak, but can be very strong for large bodies like planets. And on the scale that we are interested in, we're not really interested in the gravitational force because it's so weak on the scale. So for the next couple of weeks throughout this entire lecture series, we will basically ignore the gravitational force and it will be negligible. So don't even worry about it. Now I'll talk about some of the important characteristics of these fundamental forces. So we have, again, the four forces and their respective carriers. And now this is their relative strength. So if we say that the gluon has a strength of 1, then we can say that the photon has a strength of 10 to the minus 2. The W and the Z bosons are 10 to the minus 13, and the graviton is 10 to the minus 38. So you can see now this is why we can basically ignore the graviton, the gravitational force. It's just so much weaker compared to the gluon. Next, we have the charge. So the gluon, the photon, and the W and the Z bosons, the gluon, the photon, the Z boson, and the graviton have a charge of 0, whereas the W boson has a charge of either +1 or -1. Next is the mass. So the gluon, the photon, and the graviton are massless, but the Z boson has a mass of about 91.2 GeV per c squared, and the W boson has a mass of about 80.4 GeV per c squared. Now, if you've never seen this unit before, it might seem kind of strange, but I will actually talk about this in a later slide. So don't worry about that right now. But that is a unit of mass. Next, we have the range. So the range of a gluon is about 1 femtometer. We'll also find that this is about the size of a nucleus. So that's the reason why the nucleus is that size. The photon has a range of infinity, and that's the reason why we can see stars from millions of light years away. The W and the Z boson have a range of 10 to the minus 3 femtometers. So that's like 1,000 times smaller than the range of the gluon. And so you can kind of see how that is an internuclear force that applies just between different nuclei. And to be clear, also, a femtometer is 10 to the minus 15 meters, right? So very small. And finally, the graviton has a range of infinity. Next, we have spin. I'm not really going to talk about spin that much throughout this lecture, but it's the intrinsic angular momentum of a particle, and all bosons have an integer spin value. So the first 4 have a spin of 1, and the graviton hypothetically has a spin of 2. On the other hand, fermions have a half integer spin value, but I won't really talk about that in this lecture. Now I'll talk about the nucleon and the nucleus. So earlier, I mentioned the up and the down quarks. We can use these 2 quarks to start to build the nucleon. We'll start first with the proton. So a proton is composed of 2 up quarks and 1 down quark. These circles are the quarks, right? And these little squiggly lines between them, those are gluons, which again mediate the strong force. And first, we'll talk about some important attributes of the quark. So the quark has a fractional electric charge. The up quark has a charge of +2/3, and the down quark has a charge of -1/3. So if you do the math, a proton would then have a charge of +1. A neutron, on the other hand, has 2 down quarks and 1 up quark. So if you do the math there, you get a charge of 0. So that makes a lot of sense. There's also something called color charge. So a quark can be red, green, or blue, and they must combine to form a color neutral state and create a colorless particle. So this combination here of red, green, and blue is colorless, and so it's able to be formed. And we find that gluons interact with these quarks by exchanging color charge and binding these quarks together. And it is the interplay of color charge and gluon exchange that brings about the formation of nucleons. So, all right, we know how a nucleon is formed, but how is a nucleus put together like this? Well, there's something called the residual strong force, which is a secondary effect of the strong force. Essentially, nucleons still have some of the strong interactions influence that extend beyond their boundaries, which can then bring that nucleus together, all the nucleons together. You also can know that protons, well, they're all positive, therefore they should repel one another, right? So how exactly do the protons all stay together? Well, the nucleus is able to find some sort of balance between this residual strong force and the electrostatic repulsion. This isn't really what a nucleus looks like. The picture I'll show now isn't also really what it looks like either, but it's a bit more accurate. Essentially, there are no defined boundaries between nucleons. So it looks more like this, with all the quarks and gluons together and all of these nucleons sort of existing in that same space. Now I'll talk about the atom. So this is a very simple picture of the atom. In the center is the nucleus, which we talked about earlier. And in this space around the nucleus is the electron cloud. So electrons do not orbit the nucleus in fixed paths. Rather, they exist in orbitals, which are three-dimensional regions around the nucleus where electrons are most likely to be found, but we're not really going to talk about orbitals in this lecture. Essentially, an electron cloud is a probability distribution of finding electrons in different regions of this space. So we know also that electrons are negative and they should repel one another. So there must be something that's kind of holding it all together. And that's what the nucleus is for. It's the center of this, it's situated in the center of this electron cloud and holds this cloud together. I mentioned this a bit earlier. The atom is on the scale of 1 angstrom, or 10 to the minus 10 meters. And the nucleus is 1 femtometer, which is 10 to the minus 15 meters. So the electron cloud extends pretty far beyond the nucleus. All these electrons are pretty far spaced out. Now we know that, electrons do not orbit the nucleus in fixed paths, but we can model it in a way that it does exist in shells around the nucleus. And I'm sure most of you are familiar with this model. Essentially, we have the nucleus in the middle and different shells that contain electrons around this nucleus. So this middle, or this first shell, is called the K shell, and it can hold a maximum of 2 electrons. The next shell over is called the L shell, and it can hold a maximum of 8 electrons. And the next shell over is called the M shell. It can hold a maximum of 18 electrons, and you can have even more shells to accommodate all of the electrons that you need for the specific element. The capacity in each of these shells is 2n squared, where n is the number of shells away from the nucleus. So this K shell would have n equals 1, and so it can hold 2 times 1 squared electrons, which is 2. Also, there's this thing called valence electrons that I will talk about later. These are the electrons in the outermost shell of an atom. Now we'll talk about some of the common particles that you will see throughout this entire lecture series. You're going to see the proton, the neutron, and the electron, which I already talked about, and also the neutrino. So the rest mass of these particles are about 940 MeV per c squared for the proton and the neutron. For the electron, it's 0.511 MeV per c squared. And for the neutrino, it's 1 eV per c squared. Now this is where I'll talk about the unit. So first of all, what is an EV? That's an electron volt, which is the kinetic energy that's gained by an electron by its acceleration through a potential difference of 1 volt. This is kind of an arbitrary definition, but it's very, very precise. It has a value of 1.602 times 10 to the minus 23 joules. So we tend to use this as a unit for particles. Also, you might be wondering, why do we do MeV per C squared, right? The capital M being mega electron volts, or 10 to the 6 electron volts. Well, if you take this formula, right, which I'm sure you've all seen before, and you divide both sides by C squared, you get mass equals E over C squared. So essentially, you can represent the mass in terms of energy over C squared. It's customary in nuclear physics to measure the mass of a particle in terms of how much energy it would represent if it were converted via this formula. Next, we have the charge, which is pretty self-explanatory. The proton has a charge of +1, electron -1, and the neutron and neutrino are both neutral. And finally, we have the force carriers. So all four of these particles have the weak and the gravity force, but only the proton and the neutron have the strong force, and only the proton and the electron have the electromagnetic force. So you can see that each of these particles has different force carriers, and so they can behave differently from each other in very characteristic ways, and we can sort of exploit these differences and create detectors and experiments to measure them. Now we'll move on to the next portion of my lecture, elements and isotopes. So first, we'll just talk about the periodic table, which I'm sure you've all seen before. But essentially, this is the table. It's an arrangement of chemical elements based on atomic number and valence electrons. So first, let's sort of zoom into one of these elements and see what the notation means. So this is what one element looks like. We have the atomic number, which is the number of protons in the top left corner, and the atomic mass in that bottom part of the box. This is the number of protons and neutrons. And one element can only have one number of protons, but it can have different numbers of neutrons. And so this atomic mass is actually a weighted average of all possible masses of these elements. Now, in this table here, we have different rows and different columns that are organized in a very specific way. So the rows are called periods, and elements that are within the same row basically have an increasing atomic number. So this has atomic number of 21, this is 22, etc., right? These columns are the groups. So each column has a different number of valence electrons. This first column has 1 valence electron. This one has 2. Over here, we have 3 valence, 4, etc., up until 8 valence electrons. And these transition metals in the middle here have a unique electron configuration, so we can kind of ignore those for the valence electrons. And all of the elements that are within the same group have similar chemical behaviors. Now, this table is very useful because it represents different numbers of protons and different valence electrons, but it doesn't represent different numbers of neutrons. And first, for a bit of review, if an element has different numbers of neutrons, this is called an isotope. So I'll just go through the isotopes of hydrogen, just because it's easiest to draw on a slide. So first we have plutonium, which has only 1 proton. Deuterium has 1 proton and 1 neutron. And tritium has 1 proton and 2 neutrons. And these are all hydrogen, but they have different numbers of neutrons. Now I'll just go through some of the notations of isotopes. I'll talk about carbon just because it's a little bit more interesting to look at. So this top number here is the mass number, which is the number of protons and neutrons. But because we have now a distinct number of neutrons, we can write this as a whole number instead of a weighted average, and this distinguishes between different isotopes. This bottom number is the atomic number. It's the number of protons, and in some cases, we can just omit it because it's a bit redundant. We already know carbon has 6 protons, and same with hydrogen here. We already know it has 1 proton, which is why it's omitted here. Now, the question still holds, how do we represent different numbers of neutrons? That's where the chart of nuclides comes into play. So this chart is a table of all of the isotopes of the elements that we've discovered so far. So this x-axis here is the number of neutrons, and the y-axis is the number of protons. Now, this table on its own is a bit difficult to read, so let's just zoom into one section of the chart. I've chosen a random part of the chart to look at. You can see now that each row is a different element, right? Because they have the same proton number, and they have different neutron numbers. So these are all the isotopes of like cesium right here. And you can see the different neutron numbers for this. And if you go to this website, you can basically click on each isotope and find some information about them if you're interested. Kind of a nice thing. Now going back to this, you can see that there are different colors on this chart, and this reveals patterns of nuclear stability. So we'll just look at the black for now. The other colors we'll talk about later. But the black isotopes here are stable isotopes, so they can exist without decaying. We'll also find that there's a bit of a trend here, right? It's kind of increasing. In the beginning, you can see that it's about a 1-to-1 ratio of protons and neutrons. If you have the same number of protons and neutrons, it's pretty stable. But as you get to heavier isotopes, this line starts to kind of level out a bit. And so you find that you need more and more neutrons to be stable. It's about a 1 to 1.5 ratio for this case. Now, we'll move on to the next section of my lecture. We'll talk about some nuclear models. So one can use several models to mathematically describe the nucleus of a model. The first model I'll talk about is the liquid drop model. So we can imagine the nucleus as a drop of liquid that is being held together by some sort of force. This is sort of the way that we've been envisioning the nucleus so far, but now let's put some math to it, right? You might be wondering how exactly are all the components of this nucleus even being held together? There must be something that we can calculate, right? And that is the binding energy. So let's take a nucleus and let's try to decompose it into its constituent parts. What we find is that the mass of the nucleus is actually less than the mass of its constituent parts, which is very interesting. It must mean that there is some mass, some change in mass, we call it the mass defect, that is being converted to energy, which we call the binding energy. So if we add this component of delta M, this becomes all equal. And to find the binding energy, we just take this mass and multiply it by c squared. The binding energy is typically discussed as binding energy per nucleon, or B over A. And this is a table of the binding energy per nucleon. On this x-axis, we have the mass number, and the y-axis, we have the binding energy per nucleon. So we find that the most stable nucleus is iron, and that everything else is not as stable. And to reiterate here, a higher binding energy means it's more stable because it takes more energy to break apart the nucleus. So on the left side here, we have this fusion with this arrow pointing inwards. Essentially, the elements that are below iron want to fuse or combine together to become like iron. And on the right here, we have fission. So the elements above iron want to split down or decay to become like iron also. I'll bring back this formula here, except we replace the delta M with B over C squared. We still haven't answered the question of how do you find binding energy? Well, there's a formula for that. It's called the semi-empirical mass formula. It's based on the liquid drop model, and which in this model, all nucleons are uniformly distributed inside of the nucleus. This is the formula that we can use for that. And now I'll just go through each component of this formula. So first, there's the volume component. Like I mentioned earlier, we tend to describe the binding energy as binding energy per nuclei because this ratio B over A is almost constant for large nuclei. So for this first component, we can assume that the binding energy is proportional to A. Next is the surface component. So nucleons at the surface are not bound as tightly as the volumes, right? And so we actually have to subtract some value. We know that volume is proportional to A. We also know volume is proportional to R squared, R being the radius, or sorry, R cubed, R being the radius, and surface is proportional to R squared. So if you combine all of those things, you get surface is proportional to A to the 2/3. Next, we have the Coulombic component. So the Coulomb force is, if you recall, it's Q1 times Q2 over R. And so we can say that Z is Q1, Z minus 1 is Q2, and then we divide by A to the 1/3. One important fact to know is that the radius is proportional to A to the 1/3 also. And now we turn to experiments. We find that in experiments, the binding energy when the number of protons is equal to the number of neutrons is actually larger than the binding energy when they're not equal. So there must be some symmetry component that we subtract, and it's basically described by this factor here. Also in experiment, we find that the binding number or the binding energy when there's an even number of nucleons is higher than when there are an odd number of nucleons. And this is because of something called spin coupling. And so we can account for that by this factor here. And we can find these lowercase a constants by fitting this to experimentally measured binding energies. The next model here is the nuclear shell model. So we can understand that electrons can complete orbits without running into anything, right? We already talked about the electron shell model, where there were different shells around the nucleus. So now we have kind of an analogous model for the nucleus. We would kind of expect protons and neutrons to continuously collide with one another. They are just so close together. How do they not hit each other and thus lose energy? This kind of indicates that the Pauli exclusion principle is at play here. As a review, this principle states that two fermions cannot occupy the same quantum state. So in this, we have lower energy states filling up first. And when you have this, particles cannot take part in interactions which would lower their energy because there are no lower energy states. Therefore, they cannot be colliding in the nucleus. This kind of indicates that there is some sort of effective potential well in play here, created by the forces of all the other nucleons in the nucleus. So this is the potential well I'm talking about. We have a neutron potential well in red and a proton potential well in black. And the proton potential well is shifted up a little bit because of Coulomb repulsion. Now, what happens here is that the particles fill, like this is a bucket, from the bottom up, right? Filling those lower energy states first. Now, there's one other thing we have to describe before we can really model the energy levels of this shell model, and those are magic numbers. So, magic numbers are the number of nucleons in a nucleus that have a more stable configuration. For a nucleus, these magic numbers are 2, 8, 20, 28, 50, 82, and 126. There's also such thing as doubly magic numbers, where both the neutron number and the proton number are equal to a magic number. And these, as you can imagine, are even more stable. A really good example of doubly magic nuclei is calcium because it has two of them. So calcium has a proton number of 20, which is a magic number, right? It can also have 20 and 28 neutrons, which are also both magic numbers. And so we can see those two isotopes here in this little graph, where the this y-axis here is the binding energy above the semi-empirical mass formula. So you can see that these two isotopes have a higher binding energy, and so they are more stable. And these other isotopes in between are not as high. So now let's combine the nuclear shell model and the magic numbers. This is the energy levels of the nuclear shell model. I won't really go into detail about this, it's a bit complicated, but essentially these are the energy levels, and based on different spin values, you can get different numbers of nucleons that can exist in that respective level. So this level would have 2, and this level has 4, this one has 2, and if you add those together, you get 8, and these are the magic numbers that we find. An easier way to imagine this is, I think, is through this. So you can see the different energy levels and how much nucleons can fit in those levels, and you can get the magic numbers from that as well. Now, I'll talk a bit about the collective model. the last nuclear model. So in the liquid draw model and in the nuclear shell model, the nuclei are assumed to be spherical. However, we know that nuclei don't have to be spherical, they can actually be pretty deformed. And so if we combine the liquid drop model, which can be flexible, and the nuclear shell model, which is more rigid, we can get the collective model, which is a unified model. And in this model, the nuclei can rotate and deform and vibrate. So we can consider the nucleus as a droplet of nuclear matter with an equilibrium shape. And there are two equilibrium shapes discussed in this model. There's the spherical shape and there's the spheroidal shape. Now, I won't go into detail about all of the possible vibrations and deformations. There's just so many components to this model, but I'll just show you a nice image for each of these shapes. So we'll just look at vibrations for the spherical shape and for an angular momentum of 3. You can see here that the nucleus is kind of vibrating and deforming in these different models. As for rotations, we can only really look at the spheroidal shape. And if you rotate it across some axis, you can get all these different rotations, which is kind of cool. Now that's all I'll really talk about with these models. Next, I'll go into my final section, which is the decay and scattering processes. So I'm going to bring back this chart of nuclides. Before I mentioned the black color is all the stable particles or the stable isotopes, and all these colored sections are unstable. Now we'll talk about what these colored sections mean. So these unstable isotopes tend to decay into more stable configurations by emitting certain particles. In this yellow section, we have the alpha decay. This pink section is beta decay. And the blue section is electron capture or positron emission. And now I'll talk a bit about each of these decays and how that really works out. So first is alpha decay. You have a nucleus that emits an alpha particle. And this component here is called the parent, and this is the daughter. I will talk about that in a bit. An alpha particle has 2 protons and 2 neutrons, so it's essentially a helium-4 atom. And this is the notation that describes this decay. So you'll notice that in this decay, the number of protons and neutrons both decrease. And so if you recall this table, that's why it exists in this top right part of the chart. Both the neutrons and the protons are decreasing to kind of attain this black stable configuration. Next, we have the beta decay. So we have 2 types of beta decay. There's the beta minus decay and the beta plus decay or positron emission. In the beta minus decay, you have the parent that emits a beta particle or an electron. And what happens in this process is that a neutron, because it's losing a negative charge, it becomes positive. So a neutron is changing into a proton. And this is what I talked about a bit earlier in the beginning of this lecture, where you see that W minus boson getting emitted. This is the notation for that as well. You'll notice here that the number of protons increases and neutrons decreases, which is why, going back to this, the beta decay exists in this bottom right part, because the proton number is increasing and neutron number is decreasing to kind of get to this stable configuration. Now, the beta plus decay is very similar, but instead, the nucleus, the parent, emits a positron, which is a positively charged electron. In this process, you have a proton that's losing an electron or a positive charge, and so it becomes a neutron. So it's basically the opposite of this. You have a proton turning into a neutron. And this is the notation for that. So you'll notice here that the number of protons goes down and neutrons goes up. And so it makes sense why this is here in this top left portion, right? Neutrons going up, protons going down to kind of get to this, again, this stable configuration. Now let's talk about the electron capture. In this process, you have a nucleus that captures an electron, from the electron cloud. And this combines with the proton to make it become a neutron. And this is the notation for that. You'll see that the number of protons decreases and neutrons increases. And let's compare it to the beta plus decay, because they're essentially the same thing, where you see the parent is the same and the daughter is also the same. So that's why they both exist at that top left. I'm going to keep going back here, the top left part of this plot, because they want to get to, again, this like stable configuration. Now, those are all of the decay processes. We're now going to talk a bit about some scattering processes, which is a bit unrelated to what I've already discussed so far, but is important for the rest of the lecture series. So this is that electron shell model that we talked about earlier. And we have a gamma that comes in. A gamma, by the way, I didn't mention this before, is a photon of a certain energy. And it can essentially interact with electrons because the photon, right, mediates a force that acts on electrically charged objects. So it acts on the electrons. Now, when the gamma comes in here, it can interact with this inner shell electron and cause that electron to kind of bounce out. And that's called the photoelectric effect. The next one is a Compton scatter. The gamma comes in, interacts with an outer shell electron. And as a result, we get an X-ray coming out and this electron bouncing away. Next is pair production. We have a gamma coming in, and then we have an electron and a positron coming out of a nucleus. And finally, we have coherent scattering, where this gamma comes in, and then the gamma comes back out with a different energy. This is all I'll really talk about for this process. You'll probably see this more in later slides, in later lectures. And finally, we also have neutron scattering processes. So if we have the same atom and a neutron can come in, well, a neutron is neutral, so it does not interact with the electron cloud. It instead goes straight to the nucleus and interacts with the nucleus. So first, it can kind of just bounce off of this nucleus and not lose energy, and that's called elastic scattering. It can also bounce off the nucleus or become very close to the nucleus and lose energy and translate some energy into this nucleus and excite it, and that's called inelastic scattering. And finally, we have radiative capture, in which the nucleus or the neutron comes in and sticks to this nucleus and stays there. And as a result, it changes the isotope. And so those are all of the scattering processes that you might need to know for future lectures. And that is the end of my presentation. Thank you all so much. Let me know if you have any questions.
Thanks, Farah. That was a really nice talk. Thank you so much. Please enter your questions in the Q&A section of this webinar. And Farah, if you look at the Q&A, you will see that there are a few questions there for you. So I would invite you to choose the first one and answer it. Make sure that you read it for the audience as well.
Okay. Let's see. Okay. As per the chart of nuclides, what is the possibility of discovering new elements? So I will go back to the chart of nuclides. I believe like very often we are still discovering not new elements, but new isotopes and new elements. This chart is ever changing. If you go to that website, you can sort of see new isotopes getting added sort of to the edge, like fairly, I'm not sure how often, but you know, there are discoveries being made every so often. How are quarks red, green, and blue? Why does them being colorless allow them to form chromodynamics? Yeah, that's quantum chromodynamics, which is sort of out of the scope of this talk, but let's go back. We'll find it. Oh yeah, right here. So yeah, it's just like another thing, kind of like electric charge, but it's color charge, and it's extremely complicated. There's a whole thing called quantum chromodynamics that even I don't really fully understand. But essentially, you either have to have like red, green, and blue come together, or you can also have the anti version, which is like anti-red, anti-green, anti-blue can also make a colorless particle. So as long as you have like the right combination of colors, then it's colorless and possible to be formed. That was kind of a bad answer to that question, but it is very convoluted. Okay, let's see what else there is. Oh, I missed this one. Why is the binding energy per nucleon for helium and carbon more than the nuclides around them? Let's find that. Did I skip it? No, not yet. Oh, no, it's back here. Sorry. What's it here? No, sorry, let me find this slide. Those models. I assume you're talking about this slide, helium and carbon being more, yeah, this like strange spiking up here. I'm actually not entirely sure why that is the case. There's definitely something strange going on with these isotopes. If you wanted to chat about it later, I can definitely look into that for you and give you a better answer on that. Let's see, what does L equals 3 mean? I kind of just like, I definitely didn't explain that very well. That is angular momentum. So there are, from what I was looking at, they had different vibrational states for angular momentum of 0, 1, 2, and 3, and they all look very different. So just depending on that momentum, this was just the most interesting one to look at. So I chose this one. I believe the L equals 0 one, you can kind of see the size of the nucleus vibrating. So it kind of started smaller and then got bigger and smaller and bigger and smaller. As for L equals 1, I believe it was the center of the nucleus was just shifting back and forth. And then L equals 2 wasn't super interesting. I think it looked something like this. So it's just the different angular momentum of that nucleus. Why is the mass of the electron even considered when finding the binding energy? Let's go back to binding energy. In this, yeah, the mass of a nucleus or the electron is very small, so it's essentially negligible, but if you want to find a more accurate value for binding energy, then you can account for that. But yeah, compared to the proton and the neutron, it is very small. Could you please discuss more about the photonuclear effect? I assume or do you mean the photoelectric effect? Or I'm not sure if that's what you mean.
Or photonuclear when the photon interact directly with nuclei. For example, think about photofission. So it's like neutron-induced fission, but it's induced by a photon. So in some cases, photons can interact with nuclei. Or things like gamma neutron, gamma 2 neutron events, where you have, the gamma interacting with the nucleus and generating a neutron as the outcome of that interaction.
Oh yeah, thank you for that. Yeah,
Sure.
I'm sorry.
Mm-hmm.
Yeah, I guess in these slides, I was only really talking about some of the gamma scattering processes, not really a perfect picture of it, but
Yes. And indeed, photonuclear reactions have a very small cross-section. These have much higher cross-sections in general. So these are much more probable to happen.
Mm. Yeah, thank you.
Photofission has, the gamma has to have an energy of around 5 to about 10 MeV, that range. So it's higher energy photons that can induce these reactions. Yeah, but you have many questions here still, so we have a few, maybe 8 minutes left. You want to pick a couple more?
Yeah. Let's see. What is slide 25? Ah, yes. So the question is, they're asking for clarification on this slide. So, all right, there's a lot of things happening here, but essentially, we have different orbitals. There's the s orbital, the p orbital, the d, and there's also f. And each orbital corresponds to a different angular momentum. So s has L equals 0, P is L equals 1, D is L equals 2, and F is L equals 3. And with those angular momentums, you also have different spin values. So this one, so let's say this spin of like 3/2, right? Can have different, if you have like a spin of 3/2, you can also have, you can have 3/2, 1/2, -1/2, and -3/2. So there are 4 possible neutrons or protons that can be in that level, which is why we get 4. For 1/2, you can have 1/2 and -1/2, which is why you have 2. For 5/2, you can have 5/2, 3/2, 1/2, -1/2, -3/2, -5/2, which is 6 possible nucleons. Kind of a bad description of it, but essentially looking at this angular momentum and there's different spins, you can get the different number of nucleons that can exist in those levels. And then they can sort of exist in this potential well, kind of like this. Yeah, and we just find that if you sort of combine some of these levels, you can find the magic numbers, which are just happen to be more stable than other configurations. Let's see. Mm. I guess so many. Okay, I guess I'll pick one I can do. Um, so many questions. Okay, so I'll pick this question. I have an understanding of nucleons, but the principle of quarks is still confusing. I can try to clear that up for you. So if we go back to the quark. So if you remember here, this is the standard model, and we're gonna just look at the up and the down quarks. So if you want to try to build up a nucleon from that, we can just take a certain number of up quarks and down quarks, 2 up quarks for proton and 1 down quark, also for proton. And we have to do this because quarks cannot exist on their own. They have to exist in groups together, grouped together by gluons, whereas leptons actually can exist on their own. So if we take these quarks and we bring them all together, and again, we combine like color charge and electric charge and gluon exchange, you can sort of get this proton in this case. Let's see.
Laura, there was a question about your research. Folks are interested in hearing about, what research you're working on in the last couple of minutes. Maybe that would be a nice way to close this lecture.
Oh, yeah, sure. So in gamma ray detection, currently high purity germanium is being used a lot. But the issue with high purity germanium is that it has to be cooled down to cryogenic temperatures. So in my group, we're using this thing called cadmium zinc telluride, or CZT, to sort of also detect gammas. But by using CZT, we do not have to cool our detector down to cryogenic temperatures. We can just operate it at room temperature, which is really great. And what I'm working on is the electronics. So we have several ASICs, which is an application-specific integrated circuit, or like chips that are used within our detector. And so I'm going to be working on the 5th revision of our chip. Currently, we are testing the 4th revision, which I'm helping with, but hopefully we'll get some new insight with that chip, and then we can sort of improve our detector electronics, and hopefully I can be a part of that. So
Great. Great. Just a couple minutes left. I don't know if you have one last question there that you'd like to address in the Q&A.
yeah, let's see. Let's see. Okay, I guess I can answer this one. Can you explain why gammas can interact with electrons, even though gammas don't have a charge? It's a bit complicated. It's related to quantum field theory, but essentially, even though like gammas don't have a charge, they can, in the interactions with electrons, there's an exchange of virtual photons. And in this way, if you can kind of imagine like two people throwing a ball to each other, when the ball is being thrown to one person, there's like a force being exerted there. And that can be like seen as the charge, but the ball itself does not have to have any sort of charge. It's just the exchange of the ball that gives, force to the people catching it. So even though the gamma is neutral, it can still interact with charged particles.
Great. Well, I think we should finish the session now.
Yeah, we just
So I
got
want
done
to
with
thank
summer
you,
school.
Cara, very much for this very nice presentation and for answering
Yeah, I had
many
to
of these questions.
moderate this.
So, yeah.
Yeah.
Thank you so much. And I hope to see everyone here tomorrow for the next lecture. Bye, everyone.